Okay, this is the second lecture on determinants. There were only three. With determinants, it's a fascinating small topic inside linear algebra. Used to be determinants were the big thing and linear algebra was the little thing, but those changed. That situation changed. Now determinants is one specific part, a very neat little part, and my goal today is to find a formula for the determinant. It'll be a messy formula, so that's why you didn't see it right away. But if I'm given this n by n matrix, then I use those entries to create this number, the determinant. So there's a formula for it. In fact, there's another formula, a second formula using something called cofactors. So you have to know what cofactors are. And then I'll apply those formulas for some matrices that have a lot of zeros away from the three diagonals. Okay, so I'm shooting now for a formula for the determinant. You remember we started with these three properties, three simple properties, but out of that we got all these amazing facts like the determinant of AB equals determinant of A times determinant of B. But the three facts were, oh, how about I just take 2 by 2s? I know, because everybody here knows the determinant of a 2 by 2 matrix, but let's get it out of these three formulas. Okay, so here's my 2 by 2 matrix. I'm looking for a formula for this determinant, A, B, C, D. Okay, so property 1, I know what to do with the identity, right? Property 2 allows me to exchange rows, and I know what to do then. So I know that that determinant is 1. Property 2 allows me to exchange rows and know that this determinant is -1. And now I want to use property 3 to get everybody. And how will I do that? Okay, so remember that if I keep the second row the same, I'm allowed to use linearity in the first row. And I'll just use it in a simple way. I'll write this vector AB as A0 plus 0B. So that's one step using property 3. Linearity in the first row when the second row is the same. Okay, but now you can guess what I'm going to do next. Because I'd like to, if I can make the matrices diagonal, then I'm clearly there. So I'll take this one. Now I'll keep the first row fixed and split the second row. So that'll be an A0. And I'll split that into a C0. And keeping that first row the same, a 0D. I used, for this part, linearity. And now I'll, whoops, not plus, because I've got more coming. This one, I'll do the same. I'll keep this first row the same. And I'll split CD into C0 and 0D. Okay. Now I've got 4 easy determinants. And 2 of them are extremely, well, all 4 are extremely easy. 2 of them are so easy as to turn into 0, right? Which 2 of these determinants are 0 right away? The first guy is 0. Why is he 0? Why is that determinant nothing? Forget him? Well, it has a column of zeros. And so one way to think is, well, it's a singular matrix. For like 48 different reasons, that determinant is 0. It's a singular matrix. It has a column of zeros. It's dead. And this one is about as dead too. Column of zeros. Okay, so that's leaving us with this one. Now, how do I know its determinant following the rules? Well, I guess one of the properties that we actually got to was the determinant of that of that diagonal matrix then So I'm finally getting to that determinant is the AD, and this determinant is what? What's this one? Minus, because I would use property 2 to do a flip to make it CB, then property 3 to factor out the B, property C to factor out the C, property again to factor out the C, and that minus, and of course, finally, I got the answer that we knew we would get. But you see the method. You see the method, because it's method I'm looking for here, not just a 2 by 2 answer, but the method of doing, now I can do 3 by 3s and 4 by 4s and any size. So if you can see the method of taking each row at a time, so what would happen with 3 by 3s? Can we mentally do it rather than I write everything on the board for 3 by 3s? So what would we do if I had 3 by 3s? I would keep rows 2 and 3 the same, and I would split the first row into how many pieces? 3 pieces. I'd have an A00 and a 0B0 and a 00C or something for the first row. So I would, instead of going from 1 piece to 2 pieces to 4 pieces, I would go from 1 piece to 3 pieces to, what would it be? Each of those 3, would it be 9? Or 27? Oh, yeah, I've actually got more steps, right. I'd go to 9, but then I'd have another row to straighten out, 27. Yes, oh, God. Okay, let me say this again then. If it was 3 by 3, I would, separating out one row into 3 pieces would give me 3. Separating out the second row into 3 pieces, then I'd be up to 9. Separating out the third row into its 3 pieces, I'd be up to 27, 3 cubed pieces. But a lot of them would be 0. So now, when would they not be 0? Tell me the pieces that would not be 0. Now I will write the non-zero ones. Okay, so I have this matrix. I think I have to use these, start using these double symbols here, because otherwise I could never do n by n. Okay. Okay, so I split this up like crazy. A bunch of pieces are 0. Whenever I have a column of zeros, I know I've got zeros. When do I not have 0? When do I have, what is it that's like these guys? These are the survivors, 2 survivors there. So my question for 3 by 3 is going to be, what are the survivors? How many survivors are there? What are they? And when do I get a survivor? Well, I would get a survivor. For example, one survivor will be that one times that one times that one, with all zeros everywhere else. That would be one survivor. A11, 0, 0, 0, A22, 0, 0, 0, A33. That's like the AD survivor. Tell me another survivor. What other thing? Oh, now here you see the clue. Now, shall I just say the whole clue? That I'm having, the survivors have one entry from each row and each column. One entry from each row and column. Because if some column is missing, then I get a singular matrix. And that's one of these guys. See, you see what happened with, like this guy? Column 1 never got used in 0B, 0D. So its determinant was 0, and I forget it. So I'm going to forget those and just put, so tell me one more that would be a survivor. Well, the A11, well, here's another one. A11, 0, 0. Now, okay, that's used up. Row 1 is used. Column 1 is already used, so it better be 0. What else could I have? Where could I pick the guy? Which column shall I use in row 2? Use column 3. Because here if I use column 1 in row 1, this was like the column numbers were 1, 2, 3, right in order. Now the column numbers are going to be 1, 3, column 3, and column 2. So the row numbers are 1, 2, 3, of course. The column numbers are some permutation of 1, 2, 3. And here they come in the order 1, 3, 2. It's just like having a permutation matrix with, instead of the ones, with numbers. And actually, it's very close to having a permutation matrix because what I do eventually is I factor out these numbers, and then I have got. So what is that determinant equal? Well, I factor those numbers out, and I've got A11 times A22 times A33. And what does this determinant equal? Yeah, now tell me. We're really getting to the heart of these formulas now. What is that determinant? By the laws of, by our three properties, I can factor these out. I can factor out the A11, the A23, and the A32. They're in separate rows, so I can do each row separately. And then I just have to decide, is that plus sign or is that a minus sign? And the answer is it's a minus. Why minus? Because there is one row exchange to get it back to the identity. So that's a minus. Now, am I through? No, because there are other ways. What I'm really through with, what I've done, what I've completed is only the part where the A11 is there. But now I've got parts where it's A12. And now if it's A12, that row is used, that column is used. You see the idea? I could use this row and column. Now that column is used, that column is used, and this guy has to be here, A33. And what's that determinant? That's an A12 times an A21 times an A33. And does it have a plus or a minus? A minus is right. It has a minus because it's one flip away from the right order, the diagonal order. And now what's the other guy with a A12 up there? I could have used this row. I could have put this guy here and this guy here. Right? You see the whole deal? Now that's an A12, A23, A31. And does that go with a plus or a minus? Yeah, now that takes a minute of thinking, doesn't it? Because one row exchange doesn't get it in line. So what is the answer for this, plus or minus? Plus, because it takes two exchanges. I could exchange rows 1 and 3, and then 2 and 3. Two exchanges makes this thing a plus. Okay, and then finally we're going to have two more. 0, 0, A13, A21, 0, 0, 0, A32, 0, and one more guy, 0, 0, A13, 0, A22, 0, A31, 0, 0. And let's put down what we get from those. An A13, an A21, and an A32, and I think that one is a plus. And this guy is a minus because one exchange would order it. And that's a minus. All right, that has taken one whole board just to do the 3 by 3. But do you agree that we now have a formula for the determinant which came from the three properties and must be it? And I'm going to keep that formula. That's a famous, that 3 by 3 formula is one that, if the cameras will follow me back to the beginning here, I I get the ones with the plus sign are the ones that go down, like down this way, and the ones with the minus signs are sort of the ones that go this way. I won't make that precise. For two reasons. One, it would clutter up the board, and second reason, it wouldn't be right for 4x4s. For 4x4, let me just say right away, 4x4 matrix, the cross diagonal, the wrong diagonal, happens to come out with a plus sign. Why is that? If I have a 4x4 matrix with ones coming on the counter diagonal, that determinant is plus. Why? Why plus for that guy? Because if I exchange rows 1 and 4, and then I exchange rows 2 and 3, I've got the identity, and I did 2 exchanges. So this down to this, like, down toward Miami and down toward LA stuff is like 3x3 only. Okay. But I do want to get now, I don't want to go through this for 4x4s. I do want to get now the general formula. So this is what I refer to in the book as the big formula. So now this is the big formula for the determinant. I'm asking you to make a jump from 2x2 and 3x3 to n by n. Okay, so this will be the big formula. That the determinant of A is the sum of a whole lot of terms. And what are those terms? And is it a plus or a minus sign? And I have to tell you which it is, because this came in the 3x3 case, I had how many terms? 6, and half were plus and half were minus. How many terms are you figuring for 4x4? If I get 2 terms in the 2x2 case, 6 terms in the 3x3 case, what's that pattern? How many terms in the 4x4 case? 24. 4 factorial. Why 4 factorial? This would be a sum of n factorial terms. 24, 120, 720, whatever is after that. Okay. Half plus and half minus. And where do those n factorial terms come from? This is the moment to listen to this lecture. Where do those n factorial terms come from? They come because the guy in the first row can be chosen n ways. And after he's chosen, that's used up that column. So the one in the second row can be chosen n minus 1 ways. And after she's chosen, that second column has been used. And then the one in the third row can be chosen n minus 2 ways, and after it's chosen, notice how I'm getting these personal pronouns, but I've run out. And I'm not willing to stop with 3x3, so I'm just going to write the formula down. So the one in the first row comes from some column alpha. I don't know what alpha is. And the one in the I multiply that by somebody in the second row that comes from some different column. And I multiply that by somebody in the third row who comes from some yet different column. And then in the nth row, I don't know how to draw. Maybe omega for last. And the whole point is then that those column numbers are different. That alpha, beta, gamma, omega, that set of column numbers is some permutation of 1 to n. The n column numbers are each used once. And that gives us n factorial terms, and when I choose a term, that means I'm choosing somebody from every row and column, and then I just like the way I had this from row and column 1, row and column 2, row and column 3. So what was the alpha, beta stuff in that for that term here? Alpha was 1, beta was 2, gamma was 3. The permutation was the trivial permutation, 1, 2, 3, everybody in the right order. You see that formula? You see why I didn't want to start with that the first day, Friday. I'd rather we understood the properties, because out of this formula, presumably, I could figure out all these properties. How would I know that the determinant of the identity matrix was 1, for example, out of this formula? If A is the identity matrix, how does this formula give me a +1? You see it, right? Because almost all the terms are zeros. Which term isn't 0 if A is the identity matrix? Almost all the terms are 0 because almost all the A's are 0. The only time I'll get something is if it's A11 times A22 times A33. Only the permutation that's in the right order will give me something. It'll come with a plus sign, and the determinant of the identity is 1. So we could go back from this formula and prove everything. We could even try to prove that the determinant of AB was the determinant of A times the determinant of B. But like next week, we would still be working on it, because it's not clear from, if I took AB, my God, the entries of AB would be all these pieces. Well, probably historically it's been done, but it won't be repeated in 1806. Okay. It would be possible probably to see why the determinant of A equals the determinant of A transpose. That was another like miracle property at the end. That's an easier one which we could find. Okay. Is that all right for the big formula? I could take then a typical, let me do an example, which I'll just create. I'll take a 4x4 matrix. I'll put some 1s in and some 0s in. Okay, I don't know how many to put in, to tell the truth. I've never done this before. I don't know the determinant of that matrix. So, like, mathematics is being done for the first time in front of your eyes. What's the determinant? Well, there are 24 terms, because it's 4x4. Many of them will be 0, because I've got all those zeros there. Maybe the whole determinant is 0. I mean, is that a singular matrix? That possibility definitely exists. So one way to do it would be elimination. Actually, that would probably be a fairly reasonable way. I could use elimination. So I could go back to those properties and use elimination, eliminate it down. Do I have a row of zeros at the end of elimination? The answer is 0. I was thinking, shall I try this big formula? Okay. Let's try the big formula. Tell me one way I can go down the matrix, taking a 1 from every row and column, and make it to the end. So I get something that isn't 0. Well, one way to do it, I could take that times that times that times that. That would be 1, and I just said that comes in with what sign? Plus. That comes with a plus sign. Because that permutation, I've just written the permutation about 4, 3, 2, 1, and one exchange and a second exchange, 2 exchanges, puts it in the correct order. Keep walking away. Don't. Okay, we're executing a determinant formula here. As long as it's not periodic, of course. If he comes back, I'm in. No. All right. All right. Okay. So that would give me a plus 1. All right. Are there any others? Well, of course, we see another one here. This times this times this times this strikes us right away. So that's the order 3. The order 3. Let me make a little different mark here. 3, 2, 1, 4. And is that a plus or a minus? 3, 2, 1, 4. Is that permutation a plus or a minus permutation? It's a minus. How do you see that? What exchange shall I do to get it in the right order? If I exchange the 1 and the 3, I'm in the right order. Took one exchange to do it, so that would be a plus. That would be a minus 1. And now I don't know if there are any more here. Let's see. Let me try again, starting with this. Now I've got to pick somebody from. Oh yeah. You see what's happening. If I start there, okay, column 3 is used. So then when I go to next row, I can't use that. I must use that. Now columns 2 and 3 are used. When I come to this row, I must use that, and then I must use that. So if I start there, this is the only one I get. And similarly, if I start there, that's the only one I get. So what's the determinant? What's the determinant? 0. The determinant is 0 for that case. Because we were able to check the 24 terms. 22 of them were 0. 1 of them was plus 1. 1 of them was minus 1. Add up the 24 terms. 0 is the answer. OK. Well, I didn't know it would be 0 because I wasn't like thinking ahead. I was a little scared, actually, as that apparition went by. So, and I don't know if the camera caught that. So whether the rest of the world will realize that I was in danger or not, we don't know. But anyway, I guess he just wanted to be sure that we got the right answer, which is determinant 0. And then that makes me think, OK, the matrix must be singular. And then if the matrix is singular, maybe there's another way to see that it's singular, like find something in its null space. Or find a combination of the rows that gives 0. And like, what combination of those rows does give 0? Suppose I add rows 1 and rows 3. If I add rows 1 and rows 3, what do I get? I get a row of all 1s. Then if I add rows 2 and rows 4, I get a row of all 1s. So row 1 minus row 2 plus row 3 minus row 4 is probably the 0 row. It's a singular matrix. And I could find something in its null space the same way. That would be a combination of columns that gives 0. OK, there's an example. All right. So that's, well, that shows two things. It shows how we get the 24 terms. And it shows the great advantage of having a lot of zeros in there. OK. So we'll use this big formula, but I want to go onward now to cofactors. Onward to cofactors. Cofactors is a way of breaking up this big formula that connects this n by n. This is an n by n determinant that we just have a formula for, the big formula. So cofactors is a way to connect this n by n determinant to determinants one smaller. One smaller. And the way we want to do it is actually going to show up in this, since the 3 by 3 is the one that we wrote out in full, let me do this 3 by, so I'm talking about cofactors. And I'm going to start again with 3 by 3. And I'm going to take the exact formula, and I'm just going to write it as A11. This is the determinant I'm writing. I'm just going to say A11 times what? A11 times what? And it's A11 times A22, A33 minus A23, A32. Then I've got the A12 stuff times something. And I've got the A13 stuff times something. Do you see what I'm doing? I'm taking our big formula, and I'm saying, OK, choose column out of the first row, choose column 1, and take all the possibilities. And those extra factors will be what we'll call the cofactor, co meaning going with A11. So this, in parentheses, these are in, the cofactors are in parens. A11 times something. And I figured out what that something was by just looking back, if I can walk back here, to the A11, the one that comes down the diagonal, minus the one that comes that way. Those are the only two that used A11. So there they are, one with a plus and one with a minus. And now I can write in I could look back and see what used A12, and I can see what used A13, and those would be the cofactors of A12 and A13. Before I do that, what's this number? What is this cofactor? What is it there that's multiplying A11? Tell me what A22, A33 minus A23, A32 is for this. Do you recognize that? Do you recognize? Let's see, I'll put it here. There's the A11. That's used column 1. Then there's the other factors involve these other columns. This row is used. This column is used. So the only things left to use are these. And this formula uses them. And what's the cofactor? Tell me what it is, because you see it, and then I'll be happy you see what the idea of cofactors. It's the determinant of this smaller guy. A11 multiplies the determinant of this smaller guy. That gives me all the A11 part of the big formula. You see that? The determinant of this smaller guy is A22, A33 minus A23, A32. In other words, once I've used column 1 and row 1, what's left is all the ways to use the other n minus 1 columns and n minus 1 rows, one of each. All the other, and that's the determinant of the smaller guy of size n minus 1. So that's the whole idea of cofactors. And we just have to remember that with determinants, we've got pluses and minus signs to keep straight. Can we keep this next one straight? Let's do the next one. Okay, the next one will be, when I use A12, I'll have left, so I can't use that column anymore, but I can use A21 and A23, and I can use A31 and A33. So this one gave me A1 times that determinant. This will give me A12 times this determinant, A21, A33, minus A23, A31. So that's all the stuff involving A12, but have I got the sign right? Is the determinant of that correctly given by that, or is there a minus sign? There is a minus sign. I can follow one of these. If I do that times that times that, that was one that's showing up here, but it should have been a minus. So I'm going to build that minus sign into the cofactor. So the cofactor, so I put that minus sign in here. So because the cofactor is going to be strictly the thing that multiplies the factor. The factor is A12. The cofactor is the parens, the stuff in parentheses. So it's got the minus sign built in. And if I went on to the third guy, there would be this and this, this and this, and it would take its determinant. It would come out plus the determinant. So now I'm ready to say what cofactors are. So this would be a plus an A13 times its cofactor. And over here we had plus A11 times its determinant. And there we had the A12 times its cofactor. So the point is the cofactor is either plus or minus the determinant. So let me write that underneath them. What are cofactors? The cofactor of any number A, I, J, let's say. This is all the terms in the big formula that involve Aij. We're especially interested in A1j, the first row. That's what I've been talking about. But any row would be all right. All right, so what terms involve Aij? So it's the determinant of the n-1 matrix with row I, column J, erased. So it's a matrix of size n-1 with, of course, because I can't use this row or this column again. So I have the matrix all there. But now it's multiplied by a plus or a minus. This is the cofactor, and I'm going to call that Cij. I'll use capital C just to emphasize that these are important and emphasize that they're different from the A's. Okay, so now is it a plus or is it a minus? Because we see that in this case for A11 it was a plus, for A12, this is Ij, it was a minus. For this Ij, it was a plus. So any guess on the rule for plus or minus when we see those examples? Ij equal 1, 1 or 1, 3 was a plus. It sounds very like I plus j, odd or even. That doesn't surprise us, and that's the right answer. So it's a plus if I plus j is even. And it's a minus if I plus j is odd. So if I go along row 1 and look at the cofactors, I just take those determinants, those one smaller determinants, and they come in order plus, minus, plus, minus, plus, minus. But if I go along row 2 and take the cofactors, those subdeterminants, they would start with a minus because the 2, 1 entry, 2 plus 1 is odd, so like there's a pattern, plus, minus, plus, minus, plus, if it was 5 by 5. But then if I was doing a cofactor, then this sign would be minus, plus, minus, plus, minus, plus, minus, plus. It's sort of checkerboard. Okay. Okay, those are the signs that are given by this rule, I plus j, even or odd. And those are built into the cofactors. The thing is called a minor before you've built in the sign, but I don't care about those. Build in that sign and call it the cofactor. Okay, so what's the cofactor formula? What's the cofactor formula then? Let me come back to this board and say, what's the cofactor formula? determinant of A is, let's go along the first row. It's A11 times its cofactor. And then the second guy is A12 times its cofactor. And you just keep going to the end of the row. A1n times its cofactor. So that's cofactor formula along row 1. And if I went along row I, those ones would be i's. That's worth putting a box around. That's the cofactor formula. Do you see that? Actually, this would give me another way. I could have started the whole topic of determinants, and some people might choose to do it this way, because the cofactor formula would allow me to build up an n by n determinant out of n minus 1 size determinants, build those out of n minus 2, and so on. I could boil all the way down to 1 by 1s. So what's the cofactor formula for 2 by 2 matrices? Yeah, tell me that. What's the cofactor for? So here's the world's smallest example, practically, of a cofactor formula. Okay, let's go along row 1. I take this first guy times its cofactor. What's the cofactor of the 1, 1 entry? D, because you strike out the 1, 1 row and column, and you're left with D. Then I take this guy, B, times its cofactor. What's the cofactor of B? Is it C or it's minus C? Because I strike out this guy, I take that determinant, and then I follow the I plus J rule, and I get a minus, I get an odd, so it's B times minus C. Okay, of course it worked. And the 3 by 3 works. So that's the cofactor formula. And that is, it's a good formula to know, and now I'm feeling like, wow, I'm giving you a lot of algebra to swallow here. Last lecture gave you 10 properties. Now I'm giving you, and by the way, those 10 properties led us to a formula for the determinant, which was very important, and I haven't repeated it till now. What was that? The determinant is the product of the pivots. So the pivot formula is very important. The pivots have all this complicated mess already built in. As you did elimination to get the pivots, you built in all this horrible stuff quite efficiently. Then the big formula with the n factorial terms, that's got all the horrible stuff spread out. And the cofactor formula is like in between. It's got easy stuff times horrible stuff, basically. But it shows you how to get determinants from smaller determinants, and that's the application that I now want to make. So may I do one more example? So I remember the general idea, but I'm going to use this cofactor formula for a matrix. So here's going to be my example. I promised in the lecture outline at the very beginning to do an example, and let me do, I'm going to pick tridiagonal matrix of ones. I'm drawing here the 4 by 4. So this will be the matrix, I could call that A4. But my real idea is to do n by n, to do them all. So everybody understands what A1 and A2 are. Yeah, maybe we should just do A1 and A2 and A3 just for, so this is A4. What's the determinant of A1? What the determinant of A1. So what's the matrix A1 in this formula? It's just got that. So the determinant is 1. What's the determinant of A2? So it's just got this 2 by 2, and its determinant is 0. And then the 3 by 3, can we see its determinant? Can you take the determinant of that 3 by 3? Well, that's not quite so obvious, at least not to me. Being 3 by 3, I don't know. So here's a good example. How would you do that 3 by 3 determinant? We've got like n factorial different ways. Well, 3 factorial. So we've got 6 ways. OK. I mean, one way to do it, actually the way I would probably do it, being 3 by 3, I would use the big formula. I would say I've got a 1 from that, I've got a 0 from that, I've got a 0 from that, a 0 from that. In this direction is a -1. In that direction is a -1. I believe the answer is -1. Would you do it another way? Here's another way to do it. Look, subtract row 3 from, I'm just looking at this 3 by 3. Everybody's looking at the 3 by 3. Subtract row 3 from row 2. Determinant doesn't change, so those become zeros. OK, now use the cofactor formula. How's that? If this was now zeros, and I'm looking at this 3 by 3, use the cofactor formula. Why not use the cofactor formula along that row? Because then I take that number times its cofactor. So I take this number, let me put a box around it, times its cofactor, which is the determinant of that and that, which is what? That 2 by 2 matrix has determinant 1. So what's the cofactor? What's the cofactor of this guy here? Looking just at this 3 by 3. The cofactor of that 1 is this determinant, which is 1 times negative. So that's why the answer came out -1. OK. So I did the 3 by 3. I don't know if we want to try the 4 by 4. Yeah, I guess that was the point of my example, of course, so I have to try it. Sorry, I'm in a good mood today, so you have to stand for all the bad jokes. OK. OK, so what was the matrix? OK, now I'm ready for 4 by 4. Who wants to guess the I don't know, frankly. This 4 by 4, what's the determinant? I plan to use cofactors. OK, let's use cofactors. The determinant of A4 is, OK, let's use cofactors of the first row. Those are easier. So I multiply this number, which is the convenient 1, times this determinant. So it's 1 times this 3 by 3 determinant. Now, do you recognize that matrix? It's A3. So it's 1 times the determinant of A3. Coming along this row is a 1 times this determinant. And it goes with a plus, right? And then we have this 1. And what is its cofactor? Now I'm looking at this 3 by 3, this 3 by 3. So I'm looking at the 3 by 3 that I haven't x'd out. What is that? Oh, now it did a plus, or is it plus this determinant, this 3 by 3 determinant, or minus it? It's minus it, right? Because I'm starting in a 1, 2 position, and that's a minus. So I want minus this determinant, but these guys are x'd out. OK, so I got a 3 by 3. Well, let's use cofactors again. Use cofactors of the column, because actually we could use cofactors of columns just as well as rows because the transpose rule. So I'll take this one, which is now sitting in the plus position, times its determinant. Oh, hell. Oh, yeah. I shouldn't have said hell because it's all right. OK, 1 times the determinant. What is that matrix now that I'm taking this smaller one of? Oh, but there's a minus, right? The minus came from the fact that this was in the 1, 2 position, and that's odd. So this is a minus 1 times, and then this one is the upper left, and it's the 1, 1 position in its matrix, so plus. And what's this matrix here? Do you recognize that? That matrix is, yes, please say it, A2. And that's our formula for any case. A of any size, n, is equal to the determinant of a n minus 1. That's what came from taking the 1 in the upper corner, the first cofactor, minus the determinant of a n minus 2. What we discovered there is true for all n. I didn't even mention it, but I stopped taking cofactors when I got this one. Why did I stop? Why didn't I take the cofactor of this guy? Because he's going to get multiplied by 0, and no use wasting time. Or this one, too, the cofactor, her cofactor will be whatever that determinant is, but it'll be multiplied by 0, so I won't bother. Okay, there is the formula. And that now tells us I could figure out what A4 is now. Oh, yeah, finally I can get A4, because it's A3, which is minus 1, minus A2, which is 0, so it's minus 1. You see, we're getting kind of numbers that you might not have guessed. So our sequence right now is 1, 0, minus 1, minus 1. What's the next one in the sequence? A5. A5 is this minus this, so it is 0. What's A6? A6 is this minus this, which is 1. What's A7? I'm going to be stopped by either the time runs out or the board runs out here. Okay, A7 is this minus this, which is 1. I'll stop here because time is out, but let me tell you what we've got. These determinants have this series, 1, 0, minus 1, minus 1, 0, 1, and then it starts repeating. It's pretty fantastic. These determinants have period 6. So the determinant of A61 would be the determinant of A1, which would be 1. Okay, I hope you liked that example, a non-trivial example of a tridiagonal determinant. Thanks. See you on Wednesday.